Okay, the first sample problem in section 13.3 is going to be sample problem 1313. And this is found on page 862. Now, for the problem that we see here, we have an automobile. It weighs 4,000 pounds and it's moving down a 5-degree incline at a speed of 60 miles per hour. The brakes are going to be applied, and they're going to be applied at a constant rate, a constant braking force, and that braking force is 1,500 pounds. Okay. They want us to determine the time required for that automobile to come to a stop. Okay. So what we're going to do is we're going to use the impulse momentum approach to solve this problem. Okay. So if we go underneath, okay, our camera here, this is going to be sample problem 1313. Okay. And again, if you want to put the page, it's page 862. Right. And as far as our givens, we were given the weight, and I'm going to put of the automobile. So that's going to be WA. And that was equal to 4,000 pounds, right? The initial velocity, so V1, was identified as 60 miles per hour. And as you can imagine, we're going to have to do a little converting, but we'll do that in a bit. And then our final velocity was 0 because we come to a stop. Okay. They also let us know that as we're coming to a stop, the braking force that our car is going to see is going to be 1,500 pounds. Okay. And then additionally, they told us that the incline that this automobile is 5 degrees. And since this is an English problem, our gravity is going to be 32.2 feet per second squared, just as a reference, and we'll pop it in when we need it. Okay. Now, what they want us to find is they want us to find the time to come to a stop. Two. Right. So it's going to be T is what we need to find. Right. Okay. So as it's kind of told us, we're going to use that impulse momentum principle to solve this. So I'm just going to identify that our approach is impulse momentum. Okay. Now, since that is our approach, that means that we are going to have m times v1 plus the summation of force times time. Okay, so initial momentum, mass times velocity 1, plus the summation of the impulses, or the force times the times, is going to be equal to the momentum after. So m times v2. Okay. Now, because we know that our velocities have to be in feet per second, let's go ahead and convert that 60 miles per hour into feet per second. Okay. So my V1 is 60 miles per hour. And I know that 1 mile has 5,280 feet. Okay. So miles cancel here. And then 1 hour is equal to 3,600 seconds. So that hours cancel here. So if we multiply that out, our V1 should come out to 88 feet per second. Okay. So that'll be the value that we use in the problems when we need to. Right. So now we're ready to use this. So we're going to draw our diagram. And what we're going to do is we're going to draw a diagram for our initial momentum. Then we're going to add another diagram for our impulse. And then we're going to equal. And then one last diagram for our after momentum. Okay. So I'm going to sketch this And I'm just going to draw a rectangle representing my car. And the angle that we see this at is our 5 degrees. Okay. So at the center here, now how I am going to, I'm going to tilt my coordinate system so that my Y is here and my X is here. Does that make sense? So this is the X axis. All right. And my mass times velocity going through the geometric center, mass, I'm sorry, I'm just going to just do, do I want to do, yeah, I'll do A. MA times velocity 1. Okay. And this is going to be the momentum then of our automobile. This is just a generic, like, this is the principle or the approach. And then down here are my actual variables here. Okay. Plus, okay, now my next diagram is going to represent the impulse. Okay. So I'm going to draw my rectangle at an angle again. Okay. Representing that 5 degrees. And through the center here, just going to draw lightly my X and Y axis. Okay. Now this is going to be our forces. Okay. Times the time. Now, because this is an automobile, okay, it's 4,000 pounds, right? The weight here does have an impact on the momentum and the impulse. Okay. When it's a baseball getting hit with a bat, it's negligible to worry about the weight, but here it is significant. So at the geometric center here, we're going to show the weight of that automobile going down. Okay. So this is going to be our WA, and that will be vertical because again, even though we have our X and our Y axis tilted, our our weight will always go down towards the center of the earth. Okay. So it's going to be offset or off from that axis system. So I'll just kind of put Y and X here, right? The other force that is acting is going to be that braking force, okay? Since the automobile is going down the incline, that means that the braking force is deterring that motion. So our FB times T will be right there, okay? Now, along that line, if we look at our weight, there is an X component that acts. So if we kind of put this through here and we put a line parallel, we would have a WA X component right there. And it would be, because it's representing impulse, it would be times the time here. Okay. Now, we know that our 5 degree angle is right here. This is our 5 degrees on this side. So we could calculate what that X component would be because we know the weight is equal to 4,000 pounds, right? Okay. So what we're going to do is we're going to calculate that component so we can plug it in. Scooch this down just a little bit, and I'm going to do it on a little offshoot over here. Okay. So I can say that my WAX is going to be equal to, so this angle right here is my 5 degrees. That means this angle right here is the 5 degrees when we look at the right triangle. Okay. So if this is 5 degrees, the side opposite is our X component, and we're going to use the hypotenuse. So that's going to be the sine of 5 degrees times WA, which is 4,000 pounds. So that X component going in that direction down the incline is going to be 348.6 pounds. Okay. So that is that value right there. So we will use that when we need it in our equations. Okay. So what we've taken care of so far, as diagram wise, we've taken care of the momentum initial. plus our impulse, which includes the x component going down. So we're not going to be worrying about the weight because the only component that is, with the motion is going to be down the incline. So that x component is the one that is in that direction, and then opposing that is going to be the braking force. Okay. And now we're going to set this equal to, and we're going to do one more diagram representing the final momentum. So if we go here and we go down here and we go with our arrow, that's going to represent the MA times V2. Okay. And this is going to equal 0 because if you recall, we know that our final velocity is equal to 0. Okay, so that means that there's not going to be momentum in the end because we brake all the way to a stop. So that's going to be set equal to 0, right? So momentum 1 plus impulse is equal to momentum 2. All right. So now that we have our diagrams, we can plug all our values into our equations and solve for what we're going to find is our unknown is going to be our time. So starting right here, we know that we have mass times velocity 1, MA, the mass of the automobile times velocity 1 initial. Now, the sign of this is going to be positive because down the incline is our assigned positive x direction. So that's why this is positive. Then we're going to have a plus, okay? And I'm going to use the WAX value times T, okay? So I'm going to write it in variable form first, WAX times T. And then you're going to notice that our force, our braking force times the T, times the amount of time that it's applied, is going up, which is opposite the positive direction. So that's going to be a minus FV times T, or braking force times the time. And then it's going to be equal to mass times velocity 2, which we know to be 0 because we're coming to a stop. So there won't be momentum in the end. Now we can plug our values in. Now, the mass of our automobile is going to be the 4,000 pounds divided by gravity. So we're going to have 4,000 pounds divided by 32.2 multiplied by velocity 1. And we know that to be 88 feet per second. So this is going to be times 88 plus 348.6. Oops. Times our unknown value of T minus 1,500, which is our braking force, times T, okay? It's going to be equal to 0. So as you can see, our only unknown here is the time that it takes to come to a stop, all right? So go ahead and solve for T. I'll kind of write it out here and you can compare. You should get a value of 9.49 seconds as the amount of time that it takes to bring this automobile with those conditions, braking force, incline, to a stop. Okay, any questions on this one? If not, then I'm gonna stop our recording here.